Alrighty, our first example is going to be an algebraic example. I'm going to start off with a function f that says f of x equals x squared minus 2x minus 12. So notice that I've highlighted x in red so that we can see what the operations are for whatever it is that we plug into f. Right now I'm just plugging in x, but as we plug in different things, including another function, we're going to see that the highlighted x's are going to change into whatever happens to be inside the parentheses. For example, suppose we wanted to get the value of this function, the y value, when x is equal to 3. How would we do that? Well, we would simply replace all of the x's with 3. So if I take 3 on the left side, plug it in to the function f of 3 says, well, square the input, 3, subtract 2 times the input, which is 2 times 3, and subtract 12 from that. This becomes just a arithmetic problem at this point, and we can do the math on this and see that our answer is -9. So perhaps I might be making a graph of this function, and so I know that when x is equal to 3, that y is going to be -9. I might also want to do a change of variables for some reason. Sometimes that's a good thing to do in some application to avoid confusion or to accomplish some other purpose. In any case, I'm changing x into h in this case, and so really we're just changing all of the x's into h's. Now, if you look up at the top where I originally defined f of x, I've got x squared highlighted in yellow, I've got 2x highlighted in green, and I've got 12 highlighted in orange. And I'm doing this so that as we plug in a more complicated function, we can keep track of where things are and what's happening to what. So here I have a function g of x, and it's defined to be 5x minus 10. And I'm going to plug g of x into f by replacing x with g of x. So on the right side, all I've done is replaced x with g of x. So compare the color codes between the last line you see on the screen and the first line you see. So on our original definition of f up at the top, we have our first term is x squared, and that basically just says whatever's in the parentheses, which is x on that first line, I'm going to square it. Well, down at the bottom, I've put g of x as the input inside the parentheses, and so that gets squared, g of x squared, and that's what you see in yellow. Same thing with 2x. That's now going to be 2 times g of x. And notice that the 12 that's in orange doesn't change because there's no x involved. And so I don't have to do anything with x or g of x in that case. Now I know that g of x is 5x minus 10, so I can expand that out. On the left side, I've just written f of 5x minus 10, which is the same as f of g of x. On the right side, you notice that I've replaced g of x with 5x minus 10. So in the yellow, I have 5x minus 10 squared. Now remember that a binomial, when we square that, has to be squared by taking 5x minus 10 times 5x minus 10. We also have 2 times 5x minus 10, which we can expand out by just distributing the 2 through that binomial. And then again, the 12 at the end is not affected because there's no x involved. When we do all that, we get 25x squared minus 100x plus 100, which is equivalent to everything that's in yellow. We get 10x minus 20, which is equivalent to everything in green. And again, our 12 hasn't changed. So now we're just going to collect up a bunch of terms, simplify, and we get our answer 25x squared minus 110x plus 108, which happens to be f of g of x. So just to emphasize an issue of notation here, notice that we can write f of g of x as f compose g of x. And so what you see at the upper right of the screen, those two things are exactly equal to each other. I prefer the notation on the right because I think it shows more clearly what's getting plugged into what. But you will see sometimes that notation on the left side, so it's good to know what to do with that once you do see it. I can also say that g composed of f of x is the same as g of f of x. And so if we're given f of x and g of x, we find the composition f of g by simply plugging g into f in place of x. So that's basically what we did on the left side of the screen there. We can also find g of f of x by plugging f into g in place of x. Okay, here what we have is two graphs. We have a graph of f on the left in green and a graph of g on the right in pink. F has a definition of 2 times x to the 1/3 power. And what we're looking at on the f graph is when x is equal to 1, which you can see on the x-axis as that big blue dot, the corresponding y value is 2. So if you go to f of x equals 2 times x to the 1/3, replace x with 1, you get f of 1 equals 2 times 1 to the 1/3, or f of 1 equals 2. So graphically, we can go ahead and find the value of f using the graph starting at x equals 1 and finding that f of x equals 2. And we could do that with any value of x on the graph. If you look in the lower right corner of the green half of the screen, you'll see a table of x values and f of x values. And so we're dealing with x equals to 1. So if you go down the table a little bit to x equals 1, you'll see that indeed f of x equals 2. So what we've done here is graphically, with the graph, we could get x equals 1 and f of x equals 2. Numerically, using the table, we can get x equals 1, f of x equals 2. Now to make this a composition, we want to take that f of x value and plug it into g over on the right side. And so let's start with an algebraic example. Algebraically, f of x is 2 times x to the 1/3 power. If we plug that into g, notice that g has a definition of x squared. And so we're just going to take that 2 times x to the 1/3 power for f and square it. And so you see in the table, or the box rather, down at the lower left corner of the right side of the screen, that g of f of x is 2 times x to the 1/3 squared. Now we had x equals 1 on the left side, which gave us f of 1 equals 2. And now we're going to take f of 1 equals 2 as the input to g. And so when we take f of 1 equals 2, plug it into g, well, g says to square that number. So if we square 2, we get g of 2 equals to 4. So you can see that on the graph as well. We've taken the value of 2 from the left side, from the green side of the graph, and we've put that into the input of g over on the right side. Down in the lower right corner of the g graph, we have a table of f of x and g of f of x. So f of x is our input, and g of f of x is our output. F of x is 2 in this case because x was 1 and f of 1 was 2. So f of 1 is 2. We go down the table a little bit to f of x equals 2. We see that our output is 4, and we can see that on the graph. We can do the same thing with a different value of x. If we start over on the left side again with x equals -2, we see that our output is somewhere between -2 and -3 if we look at the graph. Looking at the table, we see x equals -2 gives us an output f of x, f of 2 actually, equals -2.52. This output from the green graph becomes the input to the pink graph, the red graph on the other side, g of x. So if we take f of -2 equals -2.52, and plug that into our g function, we see that our output is 6.35. And so this illustrates how we can do compositions both with graphs and with tables. In the case of the example we have here, we see both the graph and the table, and really one can replace the other for purposes of doing compositions for individual values of x. All right, so wrapping up, if we want to do compositions numerically or graphically, we are going to be given two functions, f and g. And notice up at the top here, I've got actually both compositions, f of g or g of f. The first thing we want to do is find the value of the inside function, which is in red in both cases. So whatever value of x is given, we plug it into the inside function, g on the left, f on the right. This can be done with a table or a graph, or we can actually plug it into the function expression using a calculator perhaps to get an actual value. Now we're going to take that number, the output of the inside function, we're going to plug that into the outside function, which is in blue. So this can also be done algebraically, numerically, or graphically. So in other words, we're going to take, if we look at the function on the left, we're going to take some value for x, plug it into g, get a number which is going to represent the value of the inside function, then we'll plug that into f, which is the outside function. So that output, once we plug it into f and figure out what that value is the value of the composition of the two functions. Now, one thing that's really important to keep in mind is that if we plug g into f and we plug f into g, usually we're not going to get the same answer. Sometimes we might, but usually we're not, and so we cannot say that those two are equal. So since we can't go in both directions, what we say is that composition is not a commutative operation.